Hi, my name is Tom, and I will present our paper, Robust Linear Regression for General Feature Distribution, which was written by me, Nir Weinberger, and Kfir Levy. In this presentation, I will talk about the problem, Robust Linear Regression with an Oblivious Adversary. I will show our approach, which is SGD-based algorithms, and I will give theoretical guarantees under relaxed conditions. I will start by defining linear regression with an oblivious adversary. Then we'll discuss our results and related work, and we'll further show our results for positive semi-definite covariance matrix and positive definite covariance matrix. Then I will show our experiments and end the presentation. The linear model is written as follows. Y is the observation and equals to the inner product between W star and X plus epsilon, where W star is a deterministic vector we would like to find, X is the random features vector, and epsilon is the random measurement noise. In the linear regression problem, a learner is given T independent and identical distribution samples denoted by a pair xi yi, and is needed to give a solution for the prediction problem or the estimation problem. In the prediction problem, the learner needs to give W, which minimizes the squared loss error, and in the estimation problem, the learner is needed to give W such that it is close to W star in the L2 sense. The linear model with an oblivious adversary is similar to the linear model plus a new term B. B is the random corruption such that the probability of B not equals to 0 is alpha. B is independent of the realization of the samples xi yi. This is the oblivious part of the oblivious adversary, and the adversary can know W star and the distributions of the features and the measurement noise. Our results are for sub-Gaussian features and measurement noise, and is given for two cases. One, if the covariance matrix is positive semi-definite and the features are centered, we can give an algorithm that solves the prediction problem. And if the covariance matrix is positive definite, then we give an algorithm that solves the estimation problem. In related work, most of them assume that the features are centered and has Gaussian distribution with a positive definite covariance matrix, and the measurement noise is also Gaussian with zero mean. Dorsey assumed that the design matrix is spread and the sum of the epsilon and B has a symmetric distribution around 0. We will only assume that the features and the measurement noise have sub-Gaussian distribution, and we also give rates for the case of positive semi-definite covariance matrix. We'll start with stricter assumptions with which we will later relax. First, we will assume that W star is in a ball B, which is a ball with radius d around the origin. We will assume that both the distributions of epsilon and x are bounded with probability 1. This will be later relaxed. We will use the Huber loss for our regression problem, which is known to be robust as it is interpolation between the L2 loss and the L1 loss. The Huber loss is parameterized by the radius parameter R, which is crucial to our algorithms. because we want that for non-corrupted samples the loss will be the L2 loss, not the L1 loss. So by first using the triangle inequality and then Cauchy-Schwarz inequality and then our assumptions, we define R to be 6D plus sigma. So we have that for any W inside the P, the ball with radius D, and non-corrupted sample, the Huber loss is the L2 loss. For our first result, where the covariance matrix is positive semi-definite, we show that low prediction error is possible only when the expectation of the features is 0. We show that if the expectation is not 0, then given two models and t samples from one of them, we cannot distinguish between those models, and thus we cannot find the underlying W star. We give a one-dimensional example where W star of the first model is 1 and for the other model is -1. Alpha is half and the features are deterministically 1 and the epsilons are deterministically 0. Thus we have that the model is Y equals to W star plus B, where M denotes the model 1 or 2. The adversary chooses his corruptions such that B of any model of one model equals to -2 times the W star of this model with probability half and 0 otherwise. Thus the observations for both models has the same distribution, so we cannot distinguish between the models. When the expectation is 0, we define LR to be the expected Huber loss over all the samples, the corrupted and non-corrupted. And we have that LR is a linear sum of f of W, which is the squared loss over the non-corrupted samples, and h of W, which is the loss over the corrupted samples. We show that h of W for any W inside the ball B is bigger or equal to h of W star. Thus, we can upper bound f of W minus f of W star by LR of W minus LR of W star. This means that if we apply projected SGD, we can further bound LR of W minus LR of W star. This is expressed in this slide. We use projected SGD initialized at the origin, and we have the following lemma, which combining with the previous lemma gives us an upper bound over the prediction problem, which means that the prediction problem is solved at a rate of 1 over square root of t. For the other result, where the covariance matrix is positive definite, we show that low estimation error is possible even for unknown expectation of the features. We start with a simpler case where the expectation is known. We write the linear model as before, but adding and subtracting the inner product between W star and the expectation of x. And we rewrite the objective function LR as the expected Huber loss, but with respect to the centered features, x minus its expectation. And we have that LR is strongly convex in B, and W star is the minimum in B. Here is a graphical intuition in one dimension of how our algorithm will work. LR is strongly convex between minus D and D, and W star is its minimum. Then, if we start from the origin and apply SGD for strongly convex functions, we will get to W star in a high rate. We will use SGD with a half suffix averaging, which by Rachlin has the following lemma. Then, by strong convexity, we can upper bound the estimation problem by the lemma we saw earlier to give this high convergence rate. For the more general case, where the expectation is not known, we will use two groups of samples. One group will be used to estimate the mean, which is denoted by mu, and the other group will be used to estimate W star. We rewrite the linear model now with mu and not the expectation of the features, and rewrite the objective function again with mu and not the expectation of the features. And we have that given mu, LR is strongly convex in B. We will run SGD in 2 steps. First we will draw T samples and compute mu. Then we will return the output of SGD with half suffix averaging given mu. And we have the following theorem which states that the estimation problem is solved at fast rate. Now for the extensions, first we will show the guarantee for the case where the x's and epsilons have sub-Gaussian distributions, and then we'll show an algorithm that is adaptive to the norm of W star when the features are symmetric. So for the sub-Gaussianity of the features and epsilons, we have the following theorem, which again show that we have fast convergence using the SGD for unknown expectation as shown previously. Here we need to change the radius parameter, which depends on C, where C is an explicit constant which depends logarithmically on kappa, rho, and sigma, where kappa and rho are the variance proxies of x and epsilon. When the norm of W star is not known, we cannot define R to be 6D plus sigma because D is not known. So we will need to use another way to find W star. By taking R to be 1 plus sigma and defining B as the unit ball around W star, we ensure that LR is strongly convex in B and W star is its minimum. Our method of estimating W star will be in 2 phases. In the first phase, we will get inside the ball with a radius third around W star, and in the second phase, we will employ projected SGD for strongly convex functions with radius third. This will guarantee that in the second phase, we will be inside the strongly convex region, and the output will have fast convergence to W star. This is what written in here. And we have that with high probability, we can solve the estimation problem in a fast rate. Here is a simple intuition of our algorithm. We start somewhere, and by employing parameter-free SGD by Carmon and Hinder, we get in a ball with radius third around W star. Then, in the second phase, we take a ball with radius third around this output of the first phase, and then we'll use SGD, projected SGD for strongly convex functions to get to W star, which is guaranteed to be inside this new ball. We made 2 experiments, one where 1% of the samples are corrupted, and the other where 70% of the samples are corrupted. And we compared to SGD over the L2 loss, centered SGD over the L2 loss, which means that we used mu, Huber SGD over the Huber loss, which is without mu, and our algorithm is centered SGD over the Huber loss, which shows that our algorithm is the only that can estimate W star. We have analyzed robust linear regression under general assumptions on the features, measurement noise, and the oblivious adversary. An important avenue for future work is to generalize the algorithms and the error bounds to more elaborated ML models. Thank you for listening.